Okay, our last talk of the session is Aaron Roth from Penn. Aaron has done foundational work in differential privacy and fairness. He's part of the Simons Institute on Fairness, and today I'll tell about uncertainty estimation. Please go ahead, Aaron.
All right, thanks. And just to make sure, can people hear me? Can you hear me? If someone could give some indication if they could hear me, that would be terrific.
Yes.
Awesome. Okay. Cool. So I'm going to talk about a line of work that I've done over the last few years.
I hear you, Aaron.
Huh? Can you hear me?
I think only those of us on Zoom can hear you.
Okay.
Megan?
Hello? Can you guys hear me?
No.
We just tested him and he's just working.
Hello, hello?
Alright, hello. I'll give us 5 minutes and then get him. So 5 minutes, we'll figure out how to get him back online.
Okay. Still only Zoom that can hear me, huh?
What she said is right.
Shuji, when you talk, or somebody else to check it with Aaron or
All right.
Again, Aaron. Be quiet. You can hear Aaron loud and clear. Let's hear what he has to say.
Okay, can you guys hear me now?
Yes, please go ahead.
All right. Thank you. I'm going to talk about a line of work I've been doing over the last few years with a bunch of people on this slide. And you should remember George, who is physically there in San Diego and has a poster, and you can ask him questions afterwards. So I want to talk about uncertainty estimation. We've got lots of really good ways of making predictions now. And the question is what predictions we should feel confident in. When we're making important predictions, we want to know on what examples we're likely to make mistakes and on what we're not. And there's various ways of doing that, but one way that I want to talk about today is the method of producing prediction sets. So rather than just producing a point prediction for like the label of an instance, I will produce a set of labels in a classification setting that would literally be a set of labels, in a regression setting that would be like a prediction interval. And my goal in doing this is to quantify my uncertainty. So the prediction set should contain the true label 95% of the time, say. And so the size of the prediction set gives me some idea of the degree of uncertainty, and the contents of the prediction set, it tells me where the uncertainty lies. Now, just to sort of orient you towards how you might think about this problem, let me give you like a 1-minute crash course in conformal prediction, which is a simple, elegant way to affix black box models with prediction sets. So first, let's just fix an arbitrary model F. It could be a classification or a regression model. For the point of this example, let's imagine it's a regression model, so it maps instances to numbers. And now pick what's called a nonconformity score, which can really be like any arbitrary function mapping examples and labels to real numbers. It could be anything, but you should think about it as telling you somehow how surprised you should be if you see a label y hat when you use your model to predict things. Okay, so this could be anything, but for example, a natural choice in a regression setting is just the absolute value difference between the prediction and the label that arrives in front of you, how different your prediction was from the label. And then you gather a holdout set that contains, a bunch of points, hopefully drawn IID from some distribution. And on all of these holdout points, you compute the nonconformity score of the points paired with their true labels. And on this, now you've got some empirical distribution of nonconformity scores. You find a 95th percentile quantile of that empirical distribution, a threshold such that 95% of the examples nonconformity scores fall below that threshold. And now on new examples, you just predict, given X, all of the labels whose nonconformity score when paired with X would fall below this threshold you found. Okay, so in this regression example, it would just be the prediction interval centered at the prediction f of X whose width was equal to this threshold tau. And it's not hard to convince yourself that if indeed your holdout set was drawn IID from the same data distribution on which your model is going to be deployed, then it does what it says on the back of the box. The chance that a new example has its label covered by the prediction set is 95% because the threshold is, is a 95% quantile of this exchangeable distribution. Now, what I want to focus on is that this is a marginal guarantee. The probability here is over the randomness of everything, over the randomness of the example, the label, the holdout set. And to sort of focus on what might be wrong with marginal guarantees, let's try to make this a little more concrete. Say, there's been a pandemic, someone arrives at the hospital, we need to make a concrete prediction. Given your features X, the doctor tells the patient, our model predicts your blood oxygen level in 24 hours time will be something, f of X. And it's an important decision it's going to be made about the patient. She asks, how sure are you? And maybe the doctor gives a 95% prediction interval that her blood oxygen level will be between some lower bound and some upper bound. And maybe this is supposed to be reassuring because all of these predictions within the interval, maybe they correspond to the same action. Don't admit to the ER. So the patient wonders, what does this mean? And in wanting to, judge whether the doctor is about to make a good decision or not, what she should hope that this means is that this is a probabilistic prediction about her as an individual, that somehow conditioned on, on everything the doctor knows about her, or at least everything that was fed into the model the doctor used to predict, there's a 95% chance that her label is covered by this interval. And you might ask, you might stay up at night, wondering, well, if we're conditioning on everything, what's the randomness over? Okay, it's a philosophical question, maybe the unrealized or unmeasured randomness of the world. But you don't have to worry about it too much because that's not what conformal prediction promises. It's sort of, if you think about it, it's impossible to give a guarantee like this. What conformal prediction and other similar techniques do is they give a marginal guarantee, which looks similar when you write it in math, but means something quite different. It's an average over people. The probability here is taken over X as well as Y. And what it means is that our system, systematically covers the label of 95% of people. Okay, it's averaging over people. And so, our patient was given this prediction interval. She might worry, I'm part of a demographic group that's maybe medically relevant that represents less than 5% of the population. Well, that's a good reason to worry because consistent with a 95% marginal prediction interval is that it always miscovers the label of this patient. And in fact, everyone who is in her population, this 95% is an average over people. Maybe it undercovers on her group and overcovers elsewhere. Now, of course, if we had different groups we cared about that were disjoint, we could just separately calibrate our predictors to each of these groups and we'd be done. But oftentimes, medically relevant groups are not going to be disjoint. You could be a member of many groups. So our patient might ask, what about for people like me? And the doctor might say, well, for African Americans under the age of 50, the 95% prediction interval is from A to B. For women with a family history of diabetes, the 95% prediction interval is from C to D. For people with egg allergies and no history of smoking, the 95% prediction interval is from E to F. And our patient might be a member simultaneously of all of these groups. And, again, consistent with a 95% marginal coverage guarantee is that A to B might be a disjoint interval from E to F, right? And even if they're not disjoint, which is the right one? Which one should I use in considering the wisdom of my decision? Okay, so this is sort of problems that come up when you have marginal guarantees. So What we want to do is give methods that have stronger than marginal guarantees. They're going to be stronger in a couple ways. Let me tell you a couple of them. So first of all, we want our coverage guarantees to be group conditional. Okay, so start by carving up the world into a bunch of different groups that you think might be medically relevant. There might be lots of them, they might intersect. For example, the 3 examples on this slide would be totally legitimate groups. You can define groups in arbitrary ways as a function of your feature space. They can intersect. The only thing we're going to ask is that they not be so specific that they contain only one person. Okay, like each group should be coarsely defined enough so that we can observe many people who are members of that group. But this isn't so hard to do when you don't insist that the groups are disjoint. And group conditional validity means that we want to give prediction sets that have 95% coverage, not just averaged over everybody, but conditional on the group. So we should be able to give a single prediction interval, a single prediction set to our patient, such that for each of these groups that she's a member of, we can simultaneously promise her that our predictions cover 95% of the labels as averaged over members of that group. That should be simultaneously true for every group she's a member of. There's another thing we can promise that I'll say less about because of the time and because it's a little bit more of a technical condition, but it's calibration. Okay, like we want our prediction intervals or prediction sets to have the correct coverage, again, not just marginally, but conditional on the prediction we make. The prediction we're making, remember, is supposed to be a conditional threshold, a conditional quantile of this non-conformity score distribution, and we want our coverage guarantees to be correct, also conditional on our prediction. That's calibration. And what we finally ask for is both of these things at the same time, called prediction set multi-validity. So we want to cover 95% of examples conditional on membership in all of these different intersecting groups, and also conditional on our prediction. And if you've heard of multi-calibration, this is multi-calibration is sort of about predicting means in a way that is conditionally correct in this way. And what we're doing here, you can think of as a quantile analog, where we're predicting these thresholds on the nonconformity score distribution, which are really quantiles of some distribution. So you can think of this as quantile multi-calibration, if those words mean anything to you. Okay. So how do you do it? Well, I don't have time to tell you much about the algorithms, but I just want to sort of flash them in front of you to convince you that it's actually extremely simple. These are practical algorithms. So the first algorithm that promises group conditional validity, but not threshold calibration, is basically as simple as you can imagine. It is only solving a single, one-shot convex optimization problem whose dimensionality is equal to the number of groups that you care about conditional coverage with respect to. Okay, so if you have 1,000 groups that you think might be medically relevant, say, or demographically relevant, maybe you're interested in fairness, you solve a single 1,000-dimensional, convex optimization problem. You're optimizing a 1,000-dimensional linear function, and the thing you're optimizing is a convex loss called pinball loss, and that's it. If you also want a threshold calibration, so these full multi-valid guarantees, group conditional coverage and threshold calibration, you can do that as well. It's no longer a one-shot convex optimization problem. It's an iterative algorithm, but it's, again, a very fast, efficient one. It doesn't have to run for very many steps. Again, quite practical and implementable. These things are implemented. Okay, and then just very quickly, basically as an ad for George's poster, you should go bug him afterwards. There's this landscape of statistics that we might want to estimate with guarantees that are stronger than marginal. And multi-calibration, if you've heard of that, sort of estimates means. And what I just described to you is an application of multi-valid quantiles. And you can ask, what else can you do? So very briefly as a teaser. So you can define a distributional property, which is basically just a way of assigning numbers to distributions. So the mean is a distributional quantity. The median is a distributional quantity. Different quantiles are distributional quantities. Variance is a distributional quantity. Some conditional value at risk is a distributional quantity. There's lots of them. And for any such statistic, a distributional property is really just a statistic of a distribution. For any such statistic, you could imagine trying to learn a predictor that, given X, tried to predict what this statistic was of the conditional label distribution on labels Y. And we could say that our predictor was multi-calibrated for the property that it was trying to predict if, when we looked at the conditional label distribution, conditional both on our prediction and on the example being a member of some group, that our prediction was correct. The property value on that conditional label distribution was the thing we predicted. Okay, so what I just described to you was basically this property for quantiles, but you could ask this for other statistics. Now, there's this nice literature on property elicitation that sort of comes out of the algorithmic game theory world, starting with really, I guess, the thesis of Nico Lambert. And a property is said to be elicitable if there's some loss function such that to find the property value on the distribution, you just minimize this loss function. You solve some regression problem. Okay, so these are also called M estimators in statistics. And so, for example, means are elicitable because you can minimize squared loss. Medians are elicitable because you can minimize absolute loss. Quantiles, but not everything is. Now, here's the characterization. If the property is elicitable, then this goal is hopeless. There are distributions such that there don't even exist calibrated predictors. On the other hand, for any property that is elicitable, then there's a simple canonical efficient algorithm such that for any collection of groups, you can get this property multi-calibration. So this is a full if and only if characterization. Okay, turns out you can do all of this stuff, not just in the nice distributional setting, but in an online adversarial setting as well. There are some tricks for calibrating things that are not elicitable if they're conditionally elicitable. I won't say more about this other than to say that you should ask George. And with that, let me stop and say thank you.
Any questions for Aaron?
I have one question. So, my background is that I know a fair bit about calibration in like neural networks, but I don't know a lot about this multi-calibration. So, my question is, how hard is it to put on like a layer of the kind of calibration that you're doing on top of like a small model? Or have you tried it, or yeah?
So let's see, the microphone is not great. So let me first check if I understood the question. Was it, how hard is it to do this kind of calibration on top of a small model?
Not, I mean, small is easier than that.
Sorry, if you could say it like maybe closer to the microphone, that would be helpful. Looks like UCSD is muted now. So I don't know what the question is, but it is, these multi-calibration techniques can be sort of applied as simple post-processings on top of any model. And in fact, their accuracy improving so long as the accuracy metric you care about is a proper loss. So if you measure squared error, then if you take whatever your favorite model is and then apply a post-processing to multi-calibrate it, first, that's easy to do. You don't have to retrain the model. And second, it's only accuracy improving.
So maybe I can follow up. Okay, can you hear me now?
I can sort of hear, but if you get like, maybe there's an echo or something.
Okay, it is okay. I guess I was going to ask if you have actually tried it and found that it improves accuracy.
Oh, yes. Yeah, these things work great. So in general, like you can get quite accurate models without this. So although these techniques do improve accuracy a little bit, the main use of the technique is not to improve accuracy, but they really improve group conditional coverage. So like, I don't have time to talk about the experiments, but yeah, like basically, if you run sort of techniques that are calibrated marginally, but not conditionally, then your sort of conditional coverage, although your marginal coverage is great, your conditional coverage is bad. And these techniques really do fix it. So here we do this with California census data. The algorithm I described is, by the way, implemented in Amazon's open source Fortuna uncertainty quantification package. So you can also play with it on your favorite data set.
Thanks, Aaron. Let's thank all the speakers. Is there a question? One more question.
Yeah, can you hear me, Aaron?
Yes, if you speak slowly and with small words.
So there was, I'm not an expert in conformal prediction, but there were these impossibility results from Rina Barber's group, which basically said that in order to do exact conditional inference, you need to put additional distributional assumptions. And I was just wondering, do you need additional assumptions on the distribution or what the density would look like or anything like that?
No, you don't. So like the thing that is impossible is the thing in this top box here. Like if you want true conditional coverage, you can't do that without assumptions. And the reason is basically because, you know, in a high dimensional space, you've probably seen on a new X 0 samples from the conditional label distribution you're interested in. The reason why we can do this without making any assumptions is because we're not conditioning on all of X. We're conditioning on membership in a group that has to be big enough that we've seen, you know, a decent number of samples from it, like 1 over epsilon squared samples from that group. You can have lots of groups with that property when they're not disjoint, but that's sort of the way around the impossibility results.
Okay, let's thank Aaron and all the other speakers.
All right, thanks.